Dear students, welcome to another lecture in Elements of Machine Design. We were considering the design of shafts and some of the problems also we have solved. Today we will solve problems, shafts. We will design shafts which are subjected to both tensile, both the bending moment and as well as the twisting moment. Here is a problem. See, a solid circular shaft is subjected to a bending moment of 3000 Newton meters. See, here it is meters, you have to convert it into millimeters, okay? And a torque of 10,000 Newton meters. This is also in Newton meter, you have to convert it in millimeter. The shaft is made of 45C8. You see, it is though the value is given, so the nomenclature of the steel is given. We are not going to use this anyway because we are not allowed to use data books in the exams. If data books are allowed, then they will not give the values, okay, because we can see from the data books. See, actually this is a carbon steel having 0.45% of weight percent of carbon and 0.8% of manganese. That is the carbon steel. Okay, this steel having ultimate tensile strength of 700 MPa. See, this is not the permissible tensile stress. Ultimate tensile stress this is. So whenever ultimate tensile stress is there, it should be divided by factor of safety to find the permissible tensile stress. This is 700 MPa, that means 700 Newton per millimeter square. And an ultimate shear stress, this is again ultimate shear stress, okay, of 500 MPa. This also should be again divided by the factor of safety to get a permissible shear stress. Assume a factor of safety of 6. So 6 will be the factor of safety with which these two will be divided to find out the permissible stresses. Determine the diameter of the shaft. See, in this case, there is bending moment also present and also torque is present. See, these are the this is the data given. M bending moment is 300 Newton meter, that is equal to 3 into 10 to the power 6 Newton millimeter, otherwise 300 into 10 to the power 3 Newton millimeters. Okay, similarly torque is 10,000 Newton meter, that is 10 into 10 to the power 6 Newton millimeter. And sigma B, what is this? Sigma ultimate stress, yeah, ultimate stress, sigma TU, it must be 700 Newton per millimeter square. Okay, and tau ultimate is 500 Newton per millimeter square. So allowable stresses or permissible stresses we have to find out first. Permissible tensile stresses are used for bending. Tensile stress, you see, bending means what? Some fibers will be in tension, some fibers will be in compression. It is a direct stress. Bending is a direct stress, so we have to compare to the tensile strength of the material. So the tensile the permissible tensile stress sigma T or the bending stress sigma B can be found out like this. This ultimate tensile stress sigma TU divided by factor of safety. Sigma TU is 700 by 6 is 116.7 Newton per millimeter square. Then we have to find out the shear stress, allowable shear stress. Allowable shear stress is ultimate shear stress upon factor of safety. Then we'll get 83.3 Newton per millimeter square. So now these are the permissible stresses given. You see, one step is more. If this is directly given in the problem, we need not do this. But here directly permissible stresses are not given, allowable stresses are not given, therefore we have found out. Then what we have to do? Now we have to see according to the maximum shear stress theory. See, in the last lecture we have derived two equations at the end, towards the end, that is torque equivalent and bending moment equivalent. So first let us find out torque equivalent. See, torque equivalent is equal to square root of m square plus t square. M is 300. You see, this 3 into 10 to the power 6 is m, bending moment, and torque is, this is only 3, this is 10, this torque is more. You see, bending moment is normally because of the self weight of the shaft and the weights of the pulleys. Okay, whereas the torque is the thing that we are transmitting. So this is 10 into 10 to the power 6. So the resultant will be a little more than this. See, 10.44. You see, now here whatever value you get now, it should be more greater than these two. See, if one is 3 and one is 10 and you are getting some value 8, you know that it is wrong. It should be more than this. Okay. So 10 to the power 10.44 into 10 to the power 6 Newton millimeter. Okay. if you have this you know this formula, torque is equivalent to pi by 16 tau d cube. So torque equivalent is pi by 16 d cube, put in this formula, and from this you can get the diameter value of the diameter. Okay, and we also know the equivalent bending moment formula is half of bracket m plus square root of m square plus d square bracket close is equal to, okay, otherwise this can be simply half of bending moment plus equivalent torque. Okay, this is because this is the equivalent torque formula. Okay, from this you find out what is the torque, bending torque, bending moment. You see, this bending moment, ordinary bending moment is 3 and equivalent bending moment will be more than 3. You see, ordinary torque how much is there, equivalent torque will be little more than that. Simple bend moment how much is there, equivalent bending moment will be more than that. This is 6.72 into 10 to the power 6 Newton millimeter. You see, everything should be in millimeters, otherwise your answers will be wrong. Okay, convert everything into millimeters. Okay, so now we know the formula. We have bending moment equivalent, that is ME is equal to pi by 32 sigma B d cube. This is the formula that we are using, and you substitute in this, you will get D to be 83.7. So now this is 83.7, and earlier what was there? Earlier came to 86. So for resisting the torque you require more diameter. So taking the larger of the two values, we have the diameter is 86, and 86 we don't know whether it will be available or not. So you can round it to 90 mm. So this 90 mm will be the selected diameter, designed diameter. Okay, let us see another problem here. A shaft made of mild steel is required to transmit 100 kilowatts. See, this is power. Kilowatts is power. Okay, not torque. Torque will be Newton meter. Okay, 100 kilowatt at 300 rpm, and it is supported at supported length of shaft is 3 meters. Supported length of the shaft means between the bearings. Support where you get support, you get the bearings. So bearings distance is 3 meters. 3 meters means what? Again you have to convert it into millimeters. 3000 millimeters. It carries two pulleys, each weighing 1500 newtons, supported at a distance of 1 meter from the ends respectively. Okay, you see, like in this figure, there is a shaft AB, and the distance between them, that means A and B are bearings. Okay, the distance between them is 3 meters. Okay, and 1 meter from either side there are weights of there are two pulleys, each is weighing same, each is weighing 1500. This is also 1500 newtons, this is also 15 newtons. From this side it also is 1 meter, that side also is 1 meter. See, when values are given like this, these values are same, this distances are same, then the figure is a little, the problem is a little easy, because we need not we need to calculate bending moment only one place, not in two places. Otherwise, if their different distances are different, so bending moment here will come different, here it will come different, then both you have to calculate, and whichever place maximum bending moment is coming, that place you have to design. Okay, but here no, bending moment at C also, D also will be same. Okay, so what are they saying? Okay, and then assuming the safe value of stress, determine the diameter of the shaft. Safe value of stress? What is the safe value of stress? You see, in this figure you have not, they have not given what is the safe value of the stress. So we have to assume, you see, at least no, you see, certain values you keep in your mind. Normally this value will be so much. You see, like that you should have in your mind. Okay, you see, anywhere here they have used, yeah, here they have assumed. See, here they have assumed shear stress, permissible shear stress is 60 Newton per mm square. At least this much you remember. See, tau is equal to 60. Otherwise, if you want to tau, they have taken 60. If you are assuming, if you are taking sigma, sigma will be more than tau, so it may be some 90 or something you can take. Okay, like that. See these values, suppose in the question is not given, you should be able to assume. Okay, again every student will assume differently. One fellow may assume only 50 Newton per millimeter square, another fellow may assume 70 Newton per millimeter square. It doesn't matter. In design, all the answers will not be the same. Okay. Okay, so they are saying determine the diameter of the shaft. Now, what is given? Power is given. Power is 100 kilowatts. You see, you should remove this K. K is a small K. Huh? Small K is kilo. Kilo means 10 to the power 3. Okay, here you should always use small k, not capital K, because capital K stands for Kelvin. That is for temperature unit. Here we always use small k. W will be capital because this is the name of the scientist. Watt, James Watt. On his name, no, the power unit is given. Okay, so 100 kilowatt means 100 into 10 to the power 3 watts. Newton, again, sorry, this is the speed is 300 rpm, and length is 3 meters, and weight is 1500 newtons. So first let us find out power when is given with the power. This is the power equation. Power equation is P is equal to 2 pi nt upon 60. Okay, rearrange it. From that you can find out torque. Torque will be 3183 Newton meters. See, this value in this power equation comes as meters because watts is in meters. I'm telling you again and again. So many times students do everything correctly, but only because of the confusion in the units, they will lose marks. See, you should remember that this coming in meters. Okay. Now, the shaft carrying two pulleys is like a simply supported beam. This is like a simply supported beam, supported at A and supported at B. Okay. The reaction at each support is, see, when this load and this load are acting downward, then here and here, only because these are the two supports, in these two supports there will be reaction. At A there will be RA reaction, at B there will be RB reaction. This is RB, this is RA. Are you seeing? So these reactions we have to find out. You see, totally downward pulls are 1500 plus 1500, 3000. Okay, and upward are RB plus RA plus RB. So RA plus RB will be 3000. So RA and RB will be same because everything is symmetric. So it can be said 2 RA is 3000. That means RA is 1500. So that's what is written here. RA is equal to RB is equal to 1500 newtons. Okay. Then a little consideration will show that the maximum bending moment lies at each pulley. That I told you, maximum bending moment will be either at C or D, because uh, for simply supported beam, at the support bending moment is 0. Okay, for cantilever it is different. Cantilever at the support only maximum bending moment, at the free end it will be 0. For the simply supported beam, at the supports it is 0, and where the pulley is there, the maximum bending moment will be there. So maximum bending moment at this place will be, if you take say if you take moments about C, then you will get moment. See, this is 1500 and this is 1. So 1500 into 1, instead of 1 you can put 1000. Okay, then directly you will get 1500 Newton millimeters. This should be in millimeters. Okay, so here this person, no, up to this point he is brought in Newton meters only. Okay, so bending moment we have got, and torque also we have got. Torque we got first 3000, around 3000. Bending moment is 1500. So torque only is more. You're seeing, because this is not the desirable thing to transmit. This is what is desired to be transmitted. Power is transmission, means torque transmission. Okay. So we know that equivalent twisting moment is square root of m square plus t square. So m is 1500 and t is this much, 3183. So it comes to 3519 Newton meter. Had you taken it millimeters, here it will be into 10 to the power 3 into 10 to the power 3. Here also into 10 to the power 3 will come. Okay, so it will be here he has converted 3519 into 10 to the power 3 Newton millimeter. Okay, we also know that the equivalent twisting moment TE formula is pi by 16 tau d cube. T is equal to pi by 16 tau d cube. So TE is submitted substituted here, and from this he has found out uh, everything. See, only tau is not there. He said you assume the safe values of stress, so we are assuming tau is equal to 60 Newton per millimeter square, and d cube is this much, and you will, from this you find out d is 66.8. 66.8 means you round it, because 66.8 diameter you may not get in the market, so you round it to 70 mm. So diameter is 70 mm. See here, this diameter we are getting considering the twisting moment, considering the equivalent torque. Okay, and you can calculate equivalent by considering the equivalent bending moment also, and which of the two is more, that you can take. Okay, that will be the final value. But in this problem, in this book, he has solved only considering the torque equivalent. Okay, now you may ask me a question: should we do for equivalent bending moment or not? You see, depending upon the number of marks, you do it. If the number of marks are less, only with the TE you finish it. If more marks are there, TE also you do, ME also you do, and then whichever of the two is maximum, that you take and you write at the end. Okay. Okay, now come to another problem. This problem is so many times asked in the exam. A line shaft is driven by means of motor placed vertically below it. You see, uh, okay, this is the shaft, and the motor is there is a pulley. This pulley has a flat belt. Okay, and the motor is down here. Okay, that means no electric motor is here, so this belt will be going like this on the motor. Okay, like that. So the pulley on the line shaft is 1.5 meters. This 1.5 meters diameter, and has a belt tension of 5.4 kilonewton and 1.8 kilonewton. You see, the belt has a tight side tension and a slack side tension. See, if it is rotating in this direction, clockwise direction, then it will be pulling and giving it here. So in this side also there will be tension in the belt, in this side also there will be tension in the belt. This is called slight tight side tension, and this side is slack side tension. Tight side tension is given by T1, slack side tension is given T2. Tight side tension is 5.4 kilonewtons, and tight slack side is 1.8 kilonewtons. Okay, respectively. Both these tensions may be assumed to be vertical. Now actually no, the pulley will be smaller pulley, and this will be going like this. But for simplification's sake, for us, otherwise you will have to take values of angle of overlap. See, now we can say angle of overlap is 180 degree if t's are straight like this. If t's are little like this, no, then you will have to take angle of overlap more than 180 degrees. Okay, and the confusion for calculations and everything, it will be little tedious. Okay, for making the matter simple, he says you take these two vertical. Okay, he is saying you take vertical. That's what this. These two tensions may be assumed to be vertical. Actually, they are not vertical, but for the simplifying of the problem, you assume to be vertical. If the pulley may be overhang from the shaft, see, this is the bearing. Here is one bearing is shown. This side another bearing will be there. I told you always shafts are mounted on two bearings only, not in three bearings. Only two bearings, not in one bearing also. Okay, because alignment problems will come if you are putting three bearings. So if because of the alignment misalignment, what will happen, ultimately load will come on two bearings only. So that's why they put only two bearings, and it cannot be supported in one bearing, because then there will be wobbling, and it will be it will not maintain its you know it cannot maintain its axis in in the proper place. A wobbling will take place. That is one. Okay, then if the pulley is overhang from the shaft. So two bearings are here, and this is an overhang. Overhang means what? It is like a cantilever. Okay, cantilever. The distance of the center line of the pulley, center line of the pulley means this is the pulley, no, this is the center line. This center line is of the shaft. You see, read properly. Center line of the pulley means center line of the pulley is here. This is the center line of the pulley. The distance between the center line of the pulley from the center line of the bearing. Center line of the bearing means this is the bearing, and this is how you should denote the bearings always. You see, like a square and cross in that. That is the bearing symbol. You know, you learned in machine drawing. Engineering. What is that? Working drawing, mechanical working drawing. Okay, this is the center of the bearing. This is the center of the pulley and the distance. You see, the bearing being 400 mm. This distance is 400 mm. Find the diameter of the shaft. So what you have to do, you have to find a diameter D of this shaft, assuming maximum allowable shear stress is 42 MPa. See, this fellow has taken only 42. In the last thing, how much did we take? Did we take 70? Maybe. So he has given 42 MPa. See, the values at least know, you should know it is 42, 50, 60, 70 like that. Okay. It is not, 1000, 2000. At least you should, approximate values you should know. Okay. Now here, no, this problem is little different because belt tensions are also involved. Okay, for belt tensions, whenever belt tensions come, two formulae you should know. One is this one. Torque is equal to T1 minus T2 into R. T1 is tight side tension, T2 is slack side tension, and R is D by 2. That is diameter of the pulley by 2. Okay, this is one. And another formula is T1 upon T2 is equal to E to the power mu theta. These two you can write and keep. These are the two formulae which will be using whenever belts are coming. Belts are coming, you have to use this. Okay, what is the data given? Diameter is given to be 1.5 meters. That means R is 0.75 meters. You can convert it into millimeters here itself so that no confusion comes later. Otherwise, you know, something is in meter, something is in millimeter, confusion will come. This is 1500. This is 750. T1 is 5.4 kilonewtons. 5.4 kilonewtons. This K should be removed. So this is 5400 newtons. T2 is 1.8 kilonewtons, means 1800 newtons. Length of the overhang of the shaft is 400 millimeters. Tau is already given 42 newton per mm square. The line shaft of the pulley is shown in the figure. You see this, sometimes no figure will be given. Sometimes you have to, from the text that you are reading, you should be able to draw the figure. Okay. So now for first formula, T is equal to T1 minus T2 into R. T1, T2, you substitute tight side tension, slack side tension, and R. So R is, if you are taking 0.75, it will be meters. If you take 750, it will come in millimeters. Okay, so this will be 2710 to the power 3. See, dear students, please see, this is not 103. It is 10 to the power 3 Newton millimeter. Sometimes, no, these people who are typing in the computer, they are careless and they won't give superscript here. This 3 should be in superscript. Okay, Newton millimeter. Then, now, neglecting the weight of the shaft. See, now, we are not considering the weight of the shaft. We are considering the weight of the, we are not even considering the weight of the pulley. Okay, only we are considering the torques. Actually, no, shaft also can have weight, pulley also can have weight. If pulley is also having some weight, you see here in this problem, you see at this place, now T1, T2, these two are down, acting down. Along with that, this W, is W given? No. Okay, see, the self weight of the pulley also will be acting down. So if this is going to bend like this, it is because not only of these two tensions, because also of the weight of the pulley. This pulley will be made of, like a steel or cast iron. If it is made of cast iron won't be like, weightless. It will have weight. Okay, so because of that weight also shaft will have bending like this. So it will be inducing bending moment. So what you should do is, so here you have to consider, if the weight is given, you have to consider. Now anyway, now weight is not given, therefore we are considering only the tight side tension and slack side tension to be pulling down. So the total weight acting at the pulley is 7200 newtons. Okay, so if that is the, and this is a cantilever sort of thing. Okay, it is a cantilever's formula for finding bending moment is, equal to the weight into the length. Okay, the weight is 7200 newtons, that is this one, and into distance is 400. So this you will get 2880 into 10 to the power 3 newton millimeter. So now you have got torque also, and you have got bending moment also. Now in this case, torque is 2700, bending moment is 2880. This is a little more, seeing compared to this. But actually, what is the desirable thing? This one. Okay, again here, equivalent torque we can find out, square root of m square plus t square. From that you will get this one, and this is torque equivalent, should be more than torque. You are seeing it is 2700, this is 3950. Okay, now you have the formula, torque equivalent is equal to pi by 16 tau d cube. From this you can find the diameter, and diameter this fellow got around 78, that means 80. And here he has designed considering only the equivalent torque, he did not consider equivalent bending moment. So it is, I told you, depending upon the marks that are allotted to the problem, you do it. Okay, now let us see shafts which are subjected to fluctuating loads. See, till now what we have seen is, we have assumed that the shaft is subjected to constant torque and constant bending moment. But in actual practice, shafts are subjected to fluctuating torque and bending moments. Fluctuations will be there. It is not a steady, torque. It is not constant torque. Okay. In order to design such shafts, like line shafts and counter shafts, the combined shock and fatigue factors must be taken into account for computing the twisting moment and the bending moment. Thus, for the shaft subjected to combined bending and torsion, equivalent twisting moment will be, see, we know that equivalent twisting moment is torque equivalent to square root of m square plus t square. But instead of m, we are multiplying it by a factor km. This is capital K and suffix m. Okay, km means this km, it is written here. What is km? Km is combined shock and fatigue factor for bending. If it is used for moment, m comes. If it is used for torque, t comes. So km and kt. Km is combined shock and fatigue factor for bending. Kt is combined shock factor for torsion. So just multiply these two things. Okay, and then you will find out. So the equivalent bending moment, similarly, this is equivalent torque. Equivalent bending moment will be me is equal to half of, you see, without km, if it is 1, km kt, if it is 1, you will get normal equation. But if you are multiplying m with km, m with km and t with kt, then you are designing for fluctuating loads. So following table recommends the values of km and kt. See km and kt values. See gradually applied load, km is 1, kt is 1. Whereas if it is suddenly applied load, km is 1.5 to 2 and kt also is 1.5 to 2. If it is rotating shafts, these are for stationary shafts. Okay, all shafts are rotating shafts. What they are telling funnily. Okay, rotating shafts gradually applied or steady, 1.5 you have to take and 1 you have to take. Whereas suddenly applied load with minor shocks and next heavy shocks. Minor shocks 1.5 to 2, heavy shocks 2 to 3, and here KT's values are given here. Okay. I think we'll stop here for today. Okay. this problem I'm keeping for some time. You try to solve it, okay, at your level. Thank you for today.